The biggest shift here is that RL for LLMs is starting to behave less like blind optimization and more like a controllable engineering system. One result shows interference between skills is often localized in shared internal routes, which means you can recover lost math or QA performance without retraining the whole model. Another turns the model itself into the environment designer, improving future training by diagnosing its own failure modes. And beneath both is a deeper question. When supervision is only coarse, trajectory-level feedback, how much learning can you still do efficiently? Let's explore the first paper, a local perturbation theory for cross-domain interference and recovery in multi-domain RL. This paper from Tianjin University and Baidu Incorporated argues that cross-domain interference in multi-domain RL for LLM post-training is a localized route-level phenomenon rather than a global gradient conflict problem. Using Qwen 3.4b, Thinking 2507, and GRPO in Virl, the authors train 4 domains: math, code, QA, and creative writing, and show that sequential code math QA CW training can drop math from 66.49 to 57.66, even while whole model gradient cosines stay near 0. Their structural analysis finds that single domain RL makes sparse, small magnitude edits, with about 77%, 89% of parameters changing by less than 1E7, while top change neurons overlap weakly across domains with Jaccard coefficients below 0.19. However, reasoning domains still share active computation routes, and directional alignment on those shared routes determines whether updates are synergistic or conflicting. The theory formalizes this as second-order local damage concentrated in a low-dimensional shared conflict subspace, and proves that a short refresh on the damaged domain geometrically contracts the harmful component. Empirically, a brief remath refresh after Sewell restores math to 66.04 and lifts the average score to 66.39, outperforming JT at 65.62 and CGPO at 65.3. A training-free rollback on a 2% proxy set of conflict coordinates recovers 20.4% of the QA-induced math loss, and a larger joint MLP plus attention rollback reaches 73.6% recovery at a 32% budget. Let's explore the second paper, From Trainee to Trainer LLM Design Training Environment for RL with Multi-Agent Reasoning. This paper, from Lark at HKUST-GZ and the University of Cambridge, reframes RL training as a closed-loop environment design problem. After each stage, the current Qwen 3.4b checkpoint becomes an LLM as environment engineer that reads structured failure breakdowns, validation history, and training context, then rewrites the next environment generator instead of selecting examples. The authors introduce MAPF Frozen Lake, a controllable, multi-agent pathfinding testbed with 3 times 3 to 10 times 10 grids and generator knobs for data, ratio, whole, ratio, and weight, ratio, trained with GRPO under an adaptive reward that combines strict path validity checks and a length penalty. On 3, 4, and 5 agent generalization benchmarks, the Qwen 3.4b plus GRPO plus hours system achieves the strongest aggregate performance, reaching 51.67 valid rate and 31.67 optimal rate on 3 agent tasks, 33, 14/21, 33 on 4 agent tasks, and 18, 67/11, 0 on 5 agent tasks, while outperforming larger proprietary LLMs, including GPT-5, 4, Grok, 4,2, Gemini, 3, OnePro, and Kimi, K2, 5 as environment designers. The analysis shows the key mechanism is evidence-driven adaptation. Successful designs preserve what already works, target specific failure modes, and concentrate training near the competence frontier rather than monotonically increasing difficulty. An ablation further shows that bookkeeping-only training details outperform full RL detail prompts, and that the current RL checkpoint is a better environment engineer than the untrained base model, indicating that policy learning improves self-diagnosis. Let's explore the third paper. When does trajectory-level supervision permit efficient offline reinforcement learning? This paper gives a sharp sample complexity theory for offline reinforcement learning when the dataset contains only trajectory-level supervision rather than per-step rewards. For the standard cumulative return objective, the authors propose OPAC, a pessimistic actor-critic method that learns a latent per-step reward from scalar trajectory labels and then optimizes a policy with layer-wise exponential weights. Under realizability and completeness, they prove a high probability sub-optimality rate of OH, 2CAC, pi n, and a matching lower bound of H, 4, epsilon, two trajectories even in deterministic two-action chains with constant concentrability, showing the axial horizon factor is the statistical price of compressing H rewards into one label. They extend the same framework to Bradley, Terry, loose trajectory preferences, preserving the leading H, 2CAC pi n dependence up to preference constant factors. Finally, for generalized trajectory objectives, they show that unrestricted nonlinear aggregation can be exponentially hard. The all-success objective requires two H trajectories. They then identify a tractable regime for Bellman recursive aggregations via two new complexity measures, the reward process coefficient kappa mi sigma and Bellman inverse coefficient chi mi sigma, and prove generalized OPAC achieves polynomial sample complexity scaling like Vmax, 2L kappa mi sigma h, 2 Cas pi, n plus Vmax, 2L chi mi sigma h, 4 n. That's a wrap on today's AI paper highlights. Thanks for watching.